Good day, dear viewers and listeners. This is episode 3 of our season 4, and in the previous episode, I talked about conformational analysis, which is one of the two types of stereoisomerisms that we have. The other type of isomerism that will be discussed today is configurational stereoisomerism. But before we proceed, do not forget to always click on the subscribe button if you have not subscribed to our YouTube channel for quality service delivery. Thank you and happy viewing and listening. So today, as I said earlier on, we shall be talking about configurational stereoisomerism. Configurational stereoisomerism is a kind of isomerism that exists between two or more molecules, whereby carbon-carbon single bond rotation or twisting is restricted, and such molecules differ in the arrangement of atoms or group in space, in three-dimensional space. So the various forms of the molecules are what we call the configurational isomers. These configurational isomers are also of two types. We have the geometric or geometrical stereoisomerism. Then we have the enantiomerism or optical isomerism. In this episode, our discussion will be fully based on geometrical isomerism. Geometric isomerism is a kind of phenomenon, or is a phenomenon that exists or whereby two or more organic molecules containing carbon-carbon double bonds have different arrangement of atoms or group in three-dimensional space. And this kind of isomerism is usually found in alkenes and their derivatives. That means for a compound to exhibit geometric isomerism, such molecule must contain carbon-carbon double bond. And the molecule must either be of this form, XY, XY, or of this form, CX, XY, XX, or of this form, C double bond, C, XY, P, Q. So that means not all compounds containing double bond can exhibit geometrical isomerism. Molecules whereby the two carbon atoms are of this form, CX2, X2, cannot exhibit geometrical isomerism when the two groups the four groups attached to the two carbon-carbon bearing double bonds are the same. And molecules of this kind, carbon-carbon double bond, XX, YY, can as well not undergo geometrical isomerism. So we are going to focus on molecules of this kind, and our first priority will be this type of organic molecules. Now, alkenes, whereby the orientation of the groups or atoms that are attached to the two carbon atoms bearing the double bonds, the way they are being arranged determines the type of geometric isomerism that the compound belongs to. We have two types. We have what we call the cis isomer, and we have the trans isomer. The cis is obtained from the Greek word cissoid, which means adjacent, while trans is from transoid, which means parallel. Now, when the two similar atoms or groups are adjacent to each other, we refer to that kind of geometric isomerism, the cis isomer. Like when you have something like this, X, Y, Y, this is the cis isomer. Why the trans isomer is when the two similar atoms or group are adjacent to each other in the two carbon atoms. So this is the trans, or the one you refer to as the transoid. Although geometric isomers usually have different physical properties at times, and their chemical properties may also be influenced by this kind of arrangement. And we want to take examples. There are several examples of that. Molecules that exhibit geometric isomerism, the cis-trans isomerism. The first is 1,2-dichloroethene, CHCl, CHCl. You have something like this, C, chlorine, chlorine, hydrogen, hydrogen. So this is cis-1,2-dichloroethene. And you have double bond C, chlorine, hydrogen, chlorine, hydrogen. This is trans 1,2-dichloroethene. Other examples are butene. You also have butene, C double bond C, CH3, hydrogen, CH3, hydrogen. This is the cis form of butene, while this is the trans form of butene. You can say this. So in terms of stability, of course you should expect one isomer to be more stable than the other. And the stability has to do with the closeness of the similar groups or the distance between them. In cis, the similar groups of atoms are much more closer to one another, and as a result of that, it creates a kind of repulsion which gives the cis isomer a higher energy and lower stability. In the trans, because they are far apart from each other, the molecules tend to to have a much more stability and a lower energy. We can also, in nature, there is what we call fumaric and malic acids. These two acids are geometric isomers of each other. One is in cis form, while the other is in trans form. If you look at this, you have something like this. C, COOH, COOH, then you have hydrogen, hydrogen. So this is but 2 in 1,4-dioic acid. Alright, this is malic acid. While the fumaric acid is of this kind, COOH, hydrogen, then you have COOH, hydrogen. This is fumaric. You can see this is the trans form, this is the cis form. And as a result of that, the orientation of the malic acid makes it possible for the molecule to undergo what we call intramolecular dehydration, resulting to malic anhydride. While this one, because the carboxyl group are far away from each other, such intramolecular reaction cannot occur in fumaric acid. So this is one of the differences between the cis and the trans isomers. And at times, they may differ in color, they may differ in terms of boiling and melting points, and other physical characteristics. Now, I want us to look at the EZ geometric isomerism. The EZ geometric isomerism. This kind of isomerism replaces the cis-trans isomers. We have the E and the Z. The E is analogous to the trans, while the Z is analogous to the cis. And in this kind of geometric isomerism is normally observed, whereby the group of atoms that are attached to the two carbon-carbon double bonds differ. Unlike in cis and trans, where they are the same. Take for instance, you have something of this nature: C, X, Y, P, Q. Now, how do you know which one is cis and which one is trans? We use what we call Kahn-Ingold Prelog system of naming in determining the configuration of this molecule, whether it is E or Z. Like for instance, how do we do that? You look at each atom or group of atoms that is attached to the carbon atom. They rank them in order of their priority. The group or atoms of higher priorities from both sides, the way they are positioned, determine whether it is E or Z. And that is also similar to what we have as cis and trans. Let us look at this as an example. You have something of this nature. Okay, let me write the two types. You have, I'm sure you can tell us the IUPAC nomenclature of this compound. Then you have something of this, C, then, bromine, then we have chlorine, OH, then we have, hydrogen here, bromine, hydrogen. Now, these are the two isomers, geometric isomers of this molecule, and that molecule is 2-bromo, 1-chloroethanol. Now in this molecule, you now determine, you rank the substituent based on the atomic number. The atomic number of bromine is 35, hydrogen is 1, chlorine is 17, oxygen is 16, which is the atom that is directly linked to the carbon atom. So here, this is rank number 1 here, this is rank number 2 here. While here, this is rank number 1, this is rank number 2. So you can see that the number 1 placed group on each carbon atom are parallel to each other. So this is the E form, which is analogous to trans. Likewise here, you have 1, 2, you have 1, 2, 2, 2, 1, 1. This is the Z isomer. There are other examples, but let us look at one more. So when you have something of that kind, that type of geometric isomerism is what we refer to as the E and Z, which is analogous to the one we are very familiar with. You have CH3, CH2, CH3. You have C, okay, CH3, 3C. And you have, let's have here, CH2, CH2, CH3. Now, how do you determine the order of priority? Of course, all of them are alkyl groups. So you are going to, since they are all alkyl groups, you consider their bulkiness or the length of the chain. This is a propyl group, this is an isobutyl group, this is a methyl group, this is an ethyl group. So this is much more bulky than this. So this should be rank number 1 on this carbon, this is rank number 2. So on this carbon, this is bulkier. 4 carbon atoms, this is less bulky. So this is rank carbon 1, this is rank carbon 2. So you can see 1, 1, 2, 2. That is the Z isomer. We can have other examples like this. You have carbon-carbon double bond. You have OH. This is an aldehyde. CH3. Then you have COOH. And you have COH. You can see. So here, the atom that is linked to this is carbon. Likewise, here you have carbon atom. So you now proceed to the next atom, which is oxygen here. And here you have hydrogen. So this must be rank 1. This must be rank 2. Likewise here, you have carbon-carbon. Next to this is oxygen. You also have oxygen here. Next on this carbon is oxygen, while next here is hydrogen. So this is the first prioritized group, while this is the second. So you have 1, 1. This is the cis isomer, which is same thing as the Z. So that is how we usually determine the nature of the molecule based on Kahn-Ingold Prelog system of determining the configuration. The geometric isomerism also exists in cyclic molecules. We also have it in cyclic molecules. A typical example is this. Just take a look at this. This is cyclohexane. If you have CH3 here, hydrogen here, then you have CH3 here, hydrogen here. Then this is another isomer of that molecule. You have CH3 here, hydrogen here, hydrogen here, CH3 here. So this is cis what? 1,4-dimethylcyclohexane, while this is trans 1,4-dimethylcyclohexane. So the geometric isomerism is a kind of isomerism which has a lot of application. One of the major applications of geometric isomerism is in the retina, which is the a vitamin aldehyde. We also call it retinaldehyde. A type of vitamin A, a kind of vitamin A that is responsible for our vision. At night, it exists in cis isomer, while during the day, when it captures certain amount of light or energy in form of photon, it stretches towards the aldehyde to form the trans isomer. So that's a lot of applications. Thank you for watching. I hope you also try to subscribe to our YouTube channel, and in next edition or episode, we are going to discuss the enantiomerism, the last type of stereoisomerism. Although that might take a lengthy time, but we are still going to get there. Thanks for watching again. I hope to see you next time. God stay blessed.